Hi, my name is Jim, and today we're going to be talking about AC switching devices, power switching devices. These are similar to MOSFETs in the DC world, but these are for AC. And there's three different components we're going to be speaking about. The first, and historically the oldest, is the silicon controlled rectifier, or SCR. The second is a triac, which is basically two SCRs in inverse parallel. So if you get this, you've got him too. And the third is a diac, which is basically a triggering diode that has some special characteristics. Now, these are called four-layer devices, where a standard transistor like an NPN would be a three-layer device. So these have four layers like NP, NP. So they're a little bit different, and I'm going to start basically by explaining what goes on inside of one. And what we need to note here is we have two transistors. Note that this is an NPN and this is a PNP. And what we need to know about this is that the current gain, called beta, or in H parameters, it's HFE for H, forward gain common emitter, but the collector current is beta times the base current, and that can be a significant increase. For example, in a 2N3904, the beta ranges from 60 to 300. Now, it's also highly dependent upon current. So that's kind of the secret to it. So if we have a circuit here with a ground, and inside the dots are the components of an SCR, and we have some load resistor here feeding 12 volts. When we apply power, typically the device will be off. Now, there's a certain exception to that, but it's rather unusual. So what I'm going to do is provide a positive going spike at the gate of this transistor. Now, what happens is that little current flowing into here is amplified by the transistor and produces a collector current flowing in this direction. So the base current flows in, collector current flows in, only the collector current is larger than the base current. Now, the collector current is also the base current of the PNP. So that base current is going to be multiplied by its beta and appears as collector current for the PNP transistor, which flows back into the base of the NPN, which in turn is amplified by the beta, which in turn is amplified by the beta, and so forth. So this is a positive feedback loop, and what it results in is a latching condition. So if this were to turn on with 12 volts, there would be nothing I could do with the gate to shut it off. So since the beta is very sensitive with regard to the current, a minimum current has to flow through this to be latched, and that is called the hold current. And if we for some reason bring it below that, the SCR will unlatch. Now, you might be thinking, well, what good is it? And for DC circuits, it's more or less correct. So let's talk about turning off. Fix this here. There we go. All better. Turning off a triac. Now, this is the trigger circuitry, and I've just shown it as a box. And let us suppose that it's turned on, and we have a path through S1, through the load resistor RL, through the SCR to ground. Well, we can turn it off by pushing down this push button, which basically breaks the path between the source voltage here, say 12 volts, and the anode of the SCR. That reduces the whole current basically to zero, turns off. Also, if we push the switch in and short out around the SCR, practically all of the current is going to flow through the switch, again going below the hold current on the SCR and turning it off. So these are the two ways of turning off DC, an SCR that's used in a DC circuit. Now, if we look at the symbol here closely, is what we see. It looks like a diode, and in fact is. It only conducts current in one direction, and that'll be when the anode is positive with respect to the cathode. So if we have a situation, say, on a positive going sine wave here, forget this part, can't conduct there because it has its diode characteristics. But what the gate will do is allow us to turn the device on anytime in quadrant 1 and quadrant 2. So the gate serves as kind of a control. Now going on kind of to show that here, this is with 60 Hertz, and we'll say that the, another mistake, SCR is triggered at 0 degrees. So what that means is that if we're starting out a sine wave, we're right here, and if we're going to trigger this and turn it on, so it's going to be turned on, and right now we're going to say that the voltage drop across it is very low. I call it V on saturation. Is what we would see if we took a look at the point B here would be 0 volts, because this is on and connected to ground, or the return on the 120 mains. Now on the second half cycle where it is off, all of the voltage would appear across the SCR. So what we need to think about then is this is basically an active load device as is the way it's wired. Now let's take a look at the load voltage. Well, if there's no voltage across the SCR essentially when it's turned on, the load voltage varies up to approximately 170 volts, which is the peak of 120. So the instantaneous value at any point of the voltage across the SCR and the load voltage have to be equal to the input voltage. And I'm thinking about 1.6 volts for saturation on this. So this is across the SCR. If it triggers here at 0 degrees, and this would be the voltage across the load, which would start at 0 degrees and end at 180 volts here. So that should sort of make sense, that this waveform would be seen across RL, load resistance, if the SCR is turned on during the first half cycle of the mains power. Okay, what if the SCR is not triggered? Okay, no trigger pulse. This is our input. This is the mains with a peak of 170, and the RMS here would be 120. And since the SCR is turned off, no current flows through this resistor. I equals 0. So 0 current times some resistor is going to be equal to 0 volt drop. So if this is a 0 volt drop, what that means is the voltage on both sides of it are going to be the same, and what we see across the SCR is basically the input waveform of the mains. Now, what's the voltage across the load? Well, if no current's flowing, the load voltage is 0. Okay, SCR triggered at 90 degrees, and kind of get the picture of the way this guy works by doing these different trigger angles. We're dealing again 120 volts RMS, 170 volts peak, and what we see is we're going to trigger the SCR at this point, 90 degrees. So this is the input waveform, and it's not triggered here, so the SCR is off. So all of the mains appears across the SCR until it's turned on. And then when it turns on, it drops basically to 0, 1.6 volts, and continues out through the rest of the cycle. Now the voltage across the load, since the SCR is turned off here, is going to be 0. And when the SCR turns on, then this will jump up at the 90 degree point, and then follow the input sine wave until we reach 180 degrees. So again, when you think about it, this should make sense that the sum of the two of these at all points have to be equal to the input waveform, or in this case the power waveform, which we call the mains with an S on it. We're never going to see anything across the load down in quadrants 3 and 4 because it's an SCR, does not conduct backward. Now, let's see if we can make sense out of this with regard to the effective voltage. And what we're going to say is we're starting with an SCR that's going to trigger at 0 degrees. And what we know about that is that the load voltage, therefore, would look like this. So the load is going to have 1/2 cycle worth of voltage on it. And if we were to compare that with PCM, with a 16.6 millisecond period, which is that of 60 hertz, basically what we're looking at here is a duty cycle of 50%. So if we're triggering and conducting 180 degrees out of 360, it's the same as 120 volts DC with a duty cycle of 50%. Okay, let's see what we have here. 120 volts triggered at 90 degrees, and what the load voltage would look like here would be this. It would trigger at 90 degrees and then jump up to about 170 and then follow the cycle through to 180 degrees, and that would correspond to PWM, 120 volts DC, again, with a 25% duty cycle. And if we did the math on this, we'd find the voltage would be about 85 volts effective. So if in our mind's eye, if we can relay the operation of an SCR to pulse width modulation, can kind of get a handle on the way the thing works. Now with an SCR, we cannot have a duty cycle greater than 50% because it does not conduct in the reverse direction. So what are we going to do about that? The question is, can an SCR control 360 degrees? Well, it can. Now, let's think about this a minute. We learned how a bridge rectifier worked, and if we have 120 volts AC coming in here, the output of the bridge without a filter, and that's really important, would look like a series of bumps where, let me see here, how do we draw this? There we go. This guy would correspond to him, and this guy would correspond to the second one, and so forth. So this is going to be 120 hertz unfiltered ripples, and since they're going from 0 to about 170 minus 2 diode drops minus the SCR drop is turned on, is we can in fact control effectively 360 degrees, and note that the output is DC. If I put a filter cap in here, I would never be able to commutate this. Now the reason that this shuts off is because this point is 0 volts. That's when the whole current goes below 0. And I need to make that point here too. Triggering at 0 degrees, shuts off right here, and then on the next half cycle, you've got to re-trigger it. Again, it's off because the hold current is below its minimum specified value. Okay, so effectively we can, and the problem with this, of course, or not, is that it is a DC output. This is unipolar. It only goes in one direction, which is positive. So it's good, but have to trigger it, of course, say somewhere in here and somewhere in here to make that happen. But we can control effectively 360 degrees with an aid of a bridge sitting in front of it. Well, what about AC? Well, suppose we put the load before the bridge and had the SCR after the bridge. And let us say that the SCR is turned on all the time. It's triggered at 0 degrees relative to the output of the bridge, which would be here, and here, and here, and here, and so forth. And what we would see that on one half cycle of the input is we would have a path through this diode, through the triggered SCR, back around through this diode, and back into 120 volt neutral. And the voltage drop across this would basically be the first half cycle of the input waveform. Now on the second half cycle, when this side is positive, we have a path in this direction through the SCR, around back up through this diode, through the load in the other direction. So that would correspond to that guy. So if we rearrange the bridge a little bit and put the load on the input side of the bridge, we can in fact switch AC with an SCR, even though it only conducts current in one direction. So that's pretty cool. Let's see, 90-degree trigger here. I don't think anything new. Oh, yeah. If this would be the voltage across the load, and suppose we're triggering at 90 degrees relative to each half cycle. So what I'm calling 90 degrees here would be this point and this point, because it is rectified by the bridge. So under the circumstances, the voltage across the load would be AC. Here it would be 0 because the SCR is not triggered. Then it is triggered, jumps up to 170 volts about, follows out the sine wave. The SCR is not triggered on the next pulse, that guy. So there's no load voltage until he is triggered, jumps up to about negative 170 volts, and so forth. So this would be kind of similar to a waveform that you would get, say, in your light dimmer in your house, except you would be using a triac instead of an SCR. So when we do that, again, the V effective is 84.85, and we'll get into that a little bit later. This would be the same as PWM with a 50% duty cycle. Okay, triacs. They can conduct in both directions, and if we look at the symbol for it, is what we can kind of see is a diode going this way and another diode going that way. So it's inverse parallel SCRs. And we have the name of the terminals here now are anode and cathode because they're truly not. This is called MT main terminal 2, and this is called main terminal 1, and then we have the gate for control again. So if we're talking about 120 volt mains and we're going to be triggering at 135 degrees, the voltage across the triac would follow the mains until it triggers. And then this guy would short out, if you will, drop to 0, and the load voltage now would be the difference between the input and the drop across the triac, jump up and follow the sine wave to its 0 volt value. Likewise, on the second half cycle, we're triggering at 135 degrees, and that translates to, if we're talking about a complete cycle, as 315 degrees, and that's really 180 plus 135, and that's relative to this point right here. So when the input waveform goes through 0, again, the whole current minimum is met, the triac turns itself off and stays off, so this voltage would be across the triac until it triggers, drops to 0, and then the rest of the voltage would be across the load, which would follow out the rest of the sine wave. So, as we can see here with a triac, is that it's built-in bidirectional. And usually the triggering is like this, symmetrical, relative to the beginning of a half cycle. Now, we can actually trigger a triac any way we want to in any quadrant, and just kind of summarize that here. If main terminal 2 is positive with respect to main terminal 1, so he's more positive than him, triggering with a positive going gate pulse is more sensitive than a negative going gate pulse. The point is, you can trigger with any polarity of input, regardless. And likewise, if main terminal 2 is more negative than main terminal 1, its gate pulse triggering is more sensitive if it's negative going, but we can still trigger positive going. So it's pretty nice that we can do that. It just takes a little bit more circuit horsepower, if you will, to trigger if the trigger voltage is opposite to that of MT2 and MT1. So when you look at this, you can kind of, I hope, get the sense of what's going on with regard to this. So if this were a light dimmer, the lights in your room would be pretty dim right now because they're only on during this time right here relative to the complete sine wave. Oh, let's see. I guess that's pretty much that page. Characteristics. So here we have an SCR. And if we run this reverse voltage, and what I mean by that is, if this is the SCR here, this is the anode, and this is the cathode. So if the anode is more negative than the cathode, that's reverse voltage across it. And if we keep increasing that, to some point, it's going to break down and fail. So if this is a 200 volt part, it would pick up a little bit of leakage. Then at 200 volts, we end up with a high voltage, high current equals high power equals fail component. Now, if this is the peak forward breakdown voltage, and we're going to trigger before we get to it, what we would see would be that the voltage of the input would follow the voltage of the input is this point until the trigger, and then it drops back close to zero, and then can rise in accordance with the current flow through the device, and the current increases, the voltage drop across the device increases too. So here we see what happens is this switchback. When the voltage goes from, say, I don't know, with a peak of 170 here, or a peak of 200, maybe this is going to be 150 volts where it triggers. When it triggers, the voltage across it drops close to zero. That's this guy. And then as the current increases, it can increase slightly with that. So the question is what happens if we don't trigger this SCR and we exceed the peak forward breakdown voltage? Is it'll switch on automatically at this point. So what will happen when current starts to flow, it'll say, oh, you know, this is trigger current, and kind of protect itself for over voltages in this direction. That is a very, very bad way to trigger. Now let's take a look at a triac, and this is no trigger applied, and what we see is that in the reverse direction, when MT2 is more negative than MT1, as we reach the breakdown voltage, current starts to flow and it turns itself on. So there's a degree of protection there. And in the forward direction with no trigger pulse, if we reach the, I'll call it the forward breakover point, current begins to flow and it'll switch itself on. So triac is a little bit more robust to over voltage and transients than is an SCR, in that it'll turn itself on and try to, I can make it sound human, try to save itself. But it's never a good thing to do that. It's always good to have an external circuit trigger the SCR or the triac. Here's the triac triggered, and this is going to be the breakdown voltages, and the trigger is going to occur here, and again the MT2 is positive with respect to MT1. We see the switchback, so the voltage here would be very small across this, and then in quadrants 3 and 4 the same thing is true. There we have a trigger before breakdown, and it switches back to a low voltage across the device when current is flowing from MT1 to main terminal 2. So that's kind of what you'd be seeing if you looked at this while we're pushing the limits on switching, and in particularly with regard to breaking the part down. Okay, diac is a triggering diode, and that's its symbol, and it's a 4-layer device also. And this is set up so that it has a breakover voltage of 34 volts or 32 volts, depending upon the model of it. And here we see it in position to trigger a triac. So what happens here is we apply 120 volts, and let me put this in here. I didn't finish my ground symbol. There we go. This is going to be our load resistance, and what we have here is kind of a phase control system. This is very similar, it is the same actually, as what you learned in AC. So we can get a phase shift here, and what that allows us to do is move the trigger point back and forth relative to the position of the positive or negative half going cycle. So we can change the angle at which it fires. So having said that, let's just assume that we're going to be charging this capacitor, and let's just say that we're on the positive half cycle, and we build up a charge across this capacitor of about 34 volts. What will happen is this thing will turn on and take this charge and dump it into the gate of this. So the gate doesn't see anything until this part, I want to use the word, breaks down. It's not a destructive breakdown, but starts to conduct, and then there's a very low resistance path into the gate, so the charge on C is dumped into the gate. So what that means is it's going to turn on very hard and very fast. We're not going to lazily raise the gate potential and the gate current until finally it turns on. We're saying now. So if we look at this, is what we'd see trigger pulses. And this would be if we elected to examine this. We can do this in the lab by putting a little resistor here and omitting this part. Because we would see the pulses be very, very quick. Up to the voltage across whatever resistor we put in the circuit, and very, very fast. So if we expanded that out, what we would see would be a typical exponential decay. So the purpose of the trigger diode is to trigger SCRs and or triacs very quickly and with a lot of gate current, so they turn on immediately. We don't want to get into those positions like we had with MOSFETs, where a slow rise and fall time on the gate produced a large amount of power as the drain voltage lazily moved down towards zero and the drain current lazily moved up to its limit from RL. We want it to be quick. So that's what a trigger diode is for, and there are several different members of the family which are do the same thing. So we'll be seeing this in lab, and actually be building a little circuit to take a look at what happens here. And that circuit would have the diac. I would have to think to get these symbols right. Feeding a resistor to ground. So when C discharges, we're able to pick up what that looks like as the voltage drop between or from this resistor to ground. And you should be seeing something like this, which is really pretty impressive. So this is the workhorse for AC power applications, our SCRs and triacs, and some of them are like that big around with a great big nut on the bottom of them, so you can really tighten them to a large heatsink. So for AC control, these are the guys that do the work. That's about it. Thank you for watching.